So Unit 9, this is our last unit for organic chemistry. We'll have our exam next week. All right, so we're going to talk about 4 functional groups today, and again, we're talking about some more reactions. We're going to cover carboxylic acids. We'll cover esters, reactions with carboxylic acids and esters. Then we'll talk about, we're going to introduce nitrogen into our organic compounds. So we'll also include the functional groups for amines and amides. So I don't know how long the lecture will go today, but we'll see. So what we're going to talk about is carboxylic acids first. So we were kind of introduced to carboxylic acids when we were talking about alcohols last chapter. Is that we take a primary alcohol, oxidize it once, so we get an aldehyde, oxidize it again, and we get a carboxylic acid. So our carboxylic acids can be written a variety of different ways that we can see here. So you're going to see all these represent carboxylic acid. So if I were to draw a carboxylic acid, we could draw something like this. We could draw the same carboxylic acid, but we could draw it, write it out like this. Let's take another carboxylic acid. We'll use it this way. Or yep, we could use it this way as well. And all of these represent the same carboxylic acid, right? The same carboxylic acid. And I want you to notice this up here, this ic acid, right? Because this is how we're going to name all of our carboxylic acids. So as far as naming our carboxylic acids, let's see here. Let's name trying to see if we should use our common ones first. Common ones first. Yeah, let's name our common ones first. So we have 2 common names. We have, let me skip to a blank page here. There we go. So let's see. We have this prefix form, which is going to represent a 1 carbon chain. And then we have our prefix acete, which represents a 2 carbon chain. All right. So if I were to draw this out, here's 1 carbon, and here is 2 carbons, right? So we're going to use these prefixes here, and we're going to end those with ic acid. Ic acid. So here we have 1 carbon, and we're going to use the prefix form, and this is formic acid. And over here, this is a 2 carbon chain, and we're going to have acetic acid, right? Using this ic acid, using this ic acid. So we have formic acid, we have acetic acid. And then we're going to come to now, and these are common. This is not IUPAC, is that these are common names, right? Common names. These are not IUPAC names. So we're only going to be sticking with just these 2 as far as the common ones, formic acid and acetic acid. So these are much different than IUPAC naming. So as far as IUPAC naming, they don't go with ic acid. They use oic acid. O. See this, right? Instead of just ic acid, they're going to use oic acid. So as we see here, here's oic acid. Here's oic acid. So we have hexane-oic acid, where we take hexane, and we remove the E, and we add our oic acid. Okay. So this is how we're going to name any of these other, when we're naming them IUPAC, not when we're naming common names, but when we're naming them with IUPAC, is we're going to add this oic acid to those. So let's see if we can go ahead and now name a couple of these out here. So here's my COOH, so I know that this is a carboxylic acid. And actually, you know what? I don't think, because of this, I don't think this is a good example. Let's not name this because we're not going to put two functional groups on the same, or what look like two functional groups on the same molecule. So let's move down below. So let's get this one down here. And we're not going to worry about anything like this. Here, so we have this benzene ring. I notice that it's a carboxylic acid, and this should be one that we memorize, and this is benzoic acid. Right? So if this is carbon number 1, this is carbon number 3, and we have 3-methyl benzoic acid. Let's check out the next one here. So this is going to be carbon number 1. And very similar to our aldehydes. When we have an aldehyde, is that here where the carbonyl is at, this is going to be carbon number 1. And here where we have our carbonyl, similar to our aldehydes, that's going to be carbon number 1. So if we go ahead and number this, 2, 3, 4, 5, 6. There was a little confusion last week when we're talking about numbering these, and I want to remind you guys that this is not a carbon, right? That's a bond between this carbon here and the carbonyl and this oxygen. That's not a carbon. So just as a reminder, there's no carbon there. Carbon number 1 is right where the carbonyl is at for a carboxylic acid. All right. So we know there's 6 carbons here, and 6 carbons represents hexane, but it's a carboxylic acid, so we're going to drop the E, and this is hexane-oic acid. On carbon number 2, I have this ethyl group, so this is 2-ethyl hexane-oic acid. So let's get some more practice in here.
I have a quick question.
Yes, sir.
Why is it a ethyl, like ending YL?
Why is this ethyl end in YL?
Yeah.
Ethyl ends because this is an alkyl branch. So here, this falls under the group of alkyl.
Okay, got it. Sorry.
And our alkyls all end in YL. So we got methyl, ethyl, propyl, butyl, right?
Yeah, I get it now.
We're good? Okay, no problem. Let's see. Let's draw some more stuff out. Yeah, go back. All right. Okay, so here, let's see what we have here. So we know it's a carboxylic acid. Carbon number 1, we'll go ahead and name these, or number these. So here, butane. And so we're going to convert this to, we drop this E, and we're going to add oic acid. So it becomes butanoic acid. Alphabetically, bromine, well, halogens are going to come before this alkyls group, but alphabetically it's going to come first anyway. So here we have 3 bromo, 2 methyl butanoic acid. Let's see. Let me see if I can mix this up a little bit. And if I put it over here, it doesn't change the fact that it's still, even though it's pointing upside down on the other side, that it still represents carbon number 1 here. So let me add some branches here. All right, so I've added some branches here. Let's number this. So heptane, we're going to drop the E. Heptanoic acid. Carbon number 2. I have methyl. Carbon number 5. I have ethyl. Carbon number 3. I have isopropyl. So ethyl's going to come first. So 5 ethyl. 3 isopropyl. 2 methyl heptanoic acid. And I think by this point, you guys should be very comfortable identifying these branches and naming them. Nothing changes about them from what we learned in Unit 7 to what we know now, is that naming all of these branches, this should be second nature by this point. Right. The only thing that we're really going to be concentrating on right now is identifying and naming the functional group, right? Because naming the branches doesn't change at all. The process we have for naming all these branches, whether it's a halogen, whether it's an alkyl group, nothing about that changes. All right. So when we think of carboxylic acids, we actually have to go back to lecture 6 when we were talking about acids and bases. If you need to go review acids and bases, that's fine. But we should remember Bronsted-Lowry acids and bases. So we know that Bronsted-Lowry acid bases is that acids are hydrogen donors, that's an R there. All right, and that bases are hydrogen acceptors, right? We also know that acids neutralize bases, bases neutralize acids. Acids react with bases, bases react with acids. And we're dealing with carboxylic acids. So we also know that these acids, all carboxylic acids are weak acids. Right, so all of our carboxylic acids are weak acids, and again, these Bronsted-Lowry acid and bases, acids are hydrogen donors, bases are hydrogen acceptors, because we're now going to start doing reactions with these carboxylic acids. So there's kind of a general formula here, and if you're worried about this, all right, believe I remind you, the R just means any random alkyl group. Doesn't matter. Doesn't really matter what the alkyl group is, right? Could be, you know, butane. There could be whatever it is. So this could be butanoic acid, pentanoic acid, hexanoic acid, heptanoic acid. There's just some random alkyl group that's attached to this in order to make it a carboxylic acid. So carboxylic acids are weak acids. And because they're weak acids, we've gone over the reaction for weak acids. That's why we see this double reaction area, because this is a reversible reaction. It can move toward the product side. It can move toward the reactant side. So once a carboxylic acid is placed in water, we get something that we call a carboxylate ion. So here, if I draw a carboxylic acid, let's actually look at a carboxylic acid. Not maybe this one below here. I'm going to draw it out a different way here. So we have CH3. I don't particularly like that COOH there. So here's a carboxylic acid. This is acetic acid. All right. We're going to add some water to it. And we're going to get this carboxylate ion. So here's our carboxylate ion. It looks like carboxylic acid. This looks like carboxylic acid, except it's missing this hydrogen here. So we have to name it differently. So this is what we know as a carboxylate ion, right? There's a charge on it, so it is an ion, and this is what we're going to consider a carboxylate. So carboxylic acid, here's a carboxylic acid, and if I want the carboxylate ion of this, I'm just going to simply remove the hydrogen and put this charge here. So here, carboxylic acid, carboxylate ion. And anytime, so this is our difference. It doesn't matter what the carboxylic acid is. There's my carboxylic acid. And if I want a carboxylate ion, I'm going to simply remove the hydrogen and place a charge there. Carboxylic acid, carboxylate. Now let's look at the naming here, because we are going to have to name these carboxylate ions. So notice this here. Ic acid. 8 ion. Is that this prefix is still the same. Only thing that happened is we dropped the ic acid and we added this 8 ion. Right? We dropped the ic acid and we put in this 8 ion. So let's try, and this is a common name. So let's do another common one that we just learned a little while ago. Is that here? This is formic acid. And if I put formic acid into water, so any carboxylic or any carboxylic acid, this is what happens to it. If we put a carboxylic acid into water, right? Carboxylic acid, carboxylate is all I'm doing is I'm going to drop that hydrogen and I'm going to add a charge to that oxygen. So here, I'm going to drop that hydrogen. I'm going to put my charge here. Plus, I'm going to get H3O plus. This is my hydrogen donor. This is my hydrogen acceptor. This is my acid. This is my base. This is my conjugate acid. This is my conjugate base. So as far as naming it, well, what do we do here? We dropped ic acid and we put 8 ion. So we're going to drop this ic acid and we're going to put formate ion. So acetic acid, acetate. Formic acid, form 8. So, excuse me. In each one of these, we're going to continue that process. Exactly. We're going to drop the IC and replace it with ATE. Now remember that our IUPAC naming is different than this common naming. If we go back to how we named it commonly, this is oic acid, oic acid. But we still follow this rule. We don't change this rule here. We're still just dropping ic acid and replacing it with ATE. The reactions are going to be the same. Here's my carboxylic acid, plus I'm going to add some water. I'm going to get my carboxylate. I'm going to drop that hydrogen. I'm going to put a charge there. So carboxylic acid, I now have my carboxylate. Plus, I have this hydronium ion here. So as far as naming this acid, this is going to be IUPAC naming. There's no common name for this. 1, 2, 3, 4. So this is not butane. I'm going to drop the E. I'm going to add oic acid. But we're still only dropping the ic acid. And this becomes butan O, because we didn't drop the O. The O is still here. All we did was drop the ic acid. So butan O, and then we're going to add ATE ion. So this is butanoic acid, butanoate. Formic acid, formate. There's no O here, so we don't put the O there, right? But here in this example down here, we don't drop the O. Okay, we do not drop the O. We're only dropping the ic acid. And every one of them is going to be done the same way. So here, let's change things up. Let's put it over on this side. Maybe we'll even add a branch here. We're going to add some water to it. Well, I need the carboxylate ion first. I'm not worried about naming it. I just want to make sure I get my carboxylate ion first. So here, so there's my carboxylate. All I've done was remove this hydrogen. I get my carboxylate ion plus I get this hydronium. All right, so now we're going to go ahead and name this. So here, originally, carbon number 1, carbon number 2, 3, 4, 5. So this is pentanoic acid. So 2-methyl pentanoic acid. And then over here, we're gonna drop the ic acid, and I have 2-methyl pentano. I'm gonna replace that ic acid with ATE ion. So 2-methylpentanoic acid to 2-methylpentanoate. Butanoic acid, butanoate. And it's just repeat that same process. We drop the hydrogen, we put our charge on there, and then we go from, we drop the ic acid, and we're simply going to go with that ATE for the conjugate base there. So here, water is acting as a base, right? So if this is my acid, this is my base, this is my conjugate base, and this is my conjugate acid, is that water is not an acid, it's not a base, but it can act as an acid, it can act as a base. So now we're going to go and work on the other concept that I mentioned earlier, where we talk about neutralizing acids and bases. So we need something more than water to neutralize an acid or base. So we're going to take our carboxylic acid and we're going to add a base to that. Acids neutralize bases, bases neutralize acids, and we get something very similar. We do get a carboxylate, but what we get is a carboxylate salt, or carboxylic acid salt. But I'm going to write carboxylate salt down here because I'm used to calling it a carboxylate salt. So carboxylate salt. But it means the same thing as a carboxylic acid salt. But I'm just used to calling it a carboxylate. So here we have our acid. This is going to be our base. And then we get our salt. Plus we get our water. All right. And this is going to neutralize that carboxylic acid. Right? It's going to neutralize that carboxylic acid. So it's very much a similar process. So here, if we go back to this process, where we take a carboxylic acid, we add it in water, we get a carboxylate ion, plus we get our hydronium here, our carboxylate. So when we neutralize, we're going to get something very similar, but here we're going to have some metal because we're neutralizing it. This is going to be our salt. Because we're going to have some metal attached to that, because we're not going to use water, we're going to actually use a base, right? So this metal here is going to be attracted, because remember, this is going to have some positive charge here, and notice that we have this negative charge over here. Let me kind of separate this over here. I don't want to think that we're talking about the same thing up there. Just something very similar. So that's what's happening over here, is that here, let me draw acetic acid out. So acetic acid So here, what we're doing is we're going to what happens here is that we're going to break this off here. How we get the water is very specific. It's not that we take either one of the hydrogens or either one of the hydroxy groups, because we notice that there's a hydroxy group here and there's a hydroxy group here, and somehow we're going to get water out of that. But it's very specific as to how we get the water. So how we get the water is we're going to break off this hydroxy group here, and then we're going to break off this hydrogen here. Right? So it's very specific how that's done. And then the result of that, let me rewrite this carboxylate salt somewhere else. It's kind of carboxylate salt. All right. So the rest of the reaction here is we're going to get some carboxylate salt. So let me get the carboxylate portion first. So here's the carboxylate, but in this reaction, because we're actually using a base, that we're not just using water, that here we're going to get a carboxylate salt. So all I've done here is I've taken this NaO and I'm just going to reverse it like this. And I'm going to add these charges to it. All right. So that's what that's the product that we have over here. So here's my carboxylate salt plus this, and this is where we're going to get our water. So we got a carboxylate salt plus we're going to get some water. So the same process occurs here, is we're going to remove this hydroxy group. We're going to remove this hydrogen. And these are going to form our water. Well, I'm going to flip this KO around to look like this. So I'm going to flip that around. I'm going to redraw. I'm going to get my carboxylate ion. I'm going to actually draw this out. This COOH is really annoying. All right, so here, I'm going to take this and I'm going to bond it over here. And I get my carboxylate salt. So I'm going to redraw this so we know what it looks like over here. All right, so all we did was we removed, right? We broke that off. And then I'm going to take this, and that's going to get bonded over here. And it's always the same reaction. It doesn't matter. It's always done the same place. The same bonds are always broken. We don't break any other bonds. Let's try another. So here's my carboxylic acid plus, let's see, sodium hydroxide. So I'm going to break this off here. I'm going to break this off here. And this is going to make my water. And then the rest of it, well, let me draw this. I'm going to draw this carboxylic acid without that OH. So I've drawn it without that OH. I'm going to take this. I'm going to flip it around. I'm going to put the charges on there. And that's what I'm going to bond here. So I get my carboxylate salt or carboxylic acid salt, plus I'm going to get some water. And every neutralization reaction for a carboxylic acid is all done the same. Doesn't matter the branches. What we have here is going to be the same reaction. Let's make it look a little bit different. We're going to break this off over here. We're going to separate this hydrogen here. And then this is going to make my water. I'm going to redraw my carboxylic acid without the OH. And now I'm going to add this other portion here. I don't have to flip it around this time, because that oxygen is going to get bonded to this number 1 carbon right here. So we'll put this right here. There we go. So This is how we get our water. This is how we get our carboxylate salt. So as far as naming these carboxylate salts, we should be able to name the carboxylate salt. Here, if we take a look at this here, I'm gonna separate this real quick. That here I have an anion, and here I have a cation, right? Let's kind of look at it. Let's kind of look at it this way. So when we're talking about, when we're naming this, well, if I asked you to name something like this, right, you could easily do that, and we call this sodium chloride, right? We name the cation, and then we name the anion, right? Sodium chloride. So we're going to use a similar process, and we know how to name this. Is that if I circle this right here, you all should know how to name this particular carboxylate, because that's all that is. That's what we were doing here, up here, right? We named all these carboxylates: formate ion, butanoate ion, 2-methyl or 2-methyl pentoate. Is that we named all of these carboxylates. Right? And that's what we're going to continue to do here, is that this is nothing more than a carboxylate. And then here we have our metal. Well, we know what the name of the metal is, so if we name the cation, then the anion, we're going to name this as potassium. And now let's name the carboxylate. 1, 2, 3, 4. So it comes from butane. Goes to butanoic acid. So here, this is butanoic acid. I'm going to drop the ic acid and add ATE. So potassium butanoate. Potassium butanoate. Let's get some more in here. All right, here's a carboxylate salt, not a carboxylic acid, because a carboxylic acid has the OH. We have a metal here. If we number these carbons, 1, 2, 3, 4, 5, 6. We name the metal first. Sodium. Instead of saying hexanoic, we're going to go hexanoate. So this is sodium hexanoate. Let's see, we can name some of these. So we could probably, we'll name this up here. Is that we're going to name the metal first. And our metal is potassium. So we have potassium, but instead of benzoic acid, benzo, we drop the ic acid and we're going to add ATE. So we get potassium benzoate. Right? Acetic acid, sodium acetate. Yes, sweetie? Yeah, I'm drawing over here. Yep. Okay. My granddaughter wants to know if I'm drawing. All right. Let's get maybe one or two more here. All right. So here we have carbon 1, 2, 3. So propane, propanoic acid. This is going to be sodium propano, and I'm going to replace the propanoic acid to propanoate. So sodium propanoate. All right. So I think that covers all of our carboxylic acids. I think maybe if we should do one more reaction. Let's do one more reaction. This is about as complex as it'll get here. How about, let me scoot this over. I'm going to need some room here. Okay. So this base, oh, you know what? I wrote it through this. There we go. So calcium hydroxide. So this is also one of your strong bases. We have 3 strong bases to memorize. Sodium hydroxide, potassium hydroxide, and calcium hydroxide. Your 3 strong bases here. So we remove the same hydroxy group. We're going to remove this hydrogen, and we're going to get we're going to take this calcium and the oxygen, and we flip it around. Oops, sorry about my screen there. But I can't put, because this is 2 plus, because it's in group 2, I'm going to put 2 plus over here, plus I'm going to get some water. The only thing we have to do here is you may see something like this on the homework. I'm pretty sure you're not going to see anything like this on the exam. This is one that's a little more complicated because let's take a look at the charges here. Calcium has a 2 plus charge, but the anion here, this hexanoate, only has 1 minus charge. Right? So the charge, so this is not actually a neutral compound just yet, but we can fix it. It's very easy to fix. So over here, if we take a look at the reactant, there's 2 hydroxy groups there because we need 2 negative charges to offset that 2 plus charge. So here we can do something very similar, and we could just put a 2 there. And that's about as complex as we're going to get. But you may see something like that on the homework. I don't know. I can't remember offhand, but just in case you do see something like that, that this is our understanding of how to balance that charge. If we need more than one of these carboxylates. But we're still going to name it the same way. So we still name it calcium. We don't use the prefix di here. This is just going to be calcium hexanoate. And that's about as complex as we'll get there. All right, so that covers, now we're covered completely done with our carboxylic acids. And just a reminder where your carboxylic acids come from is that if we take a primary alcohol, oxidize it, we get an aldehyde, oxidize that again, and we get a carboxylic acid. So your carboxylic acids come from the oxidation of an aldehyde, right? So we want to remember that information. All right. So now we're going to deal with esters. So esters also include the carboxylate. right? So we know carboxylic acids have an OH, but if we take a look at this ester, look at this. That's very familiar to us, right? That's a carboxylate, because when we name these, we're gonna use a very similar method as far as naming our carboxylates. Right. So in order to make what we call an ester, right? In order to make an ester, we use two components. So we use a carboxylic acid and we use an alcohol, right? So carboxylic acid plus an alcohol, and we get an ester plus some water. So kind of a mantra that you guys need to memorize there, right? Is that you take a carboxylic acid plus an alcohol, you get an ester. Carboxylic acid plus an alcohol, you get an ester. And notice the reaction arrow here. This is a reversible reaction, which means if I have an ester and I add some water and acid to that, here's my water, here's my acid catalyst, is that if I have an ester, I can break it down to a carboxylic acid and an alcohol. So let's look at what we call esterification, right? So esterification, taking a carboxylic acid plus some alcohol, we get our ester. So here we have one right here. So here's our carboxylic acid. Carboxylic acid plus this alcohol. So we're going to get an ester plus we're going to get some water. So let's look at where that water actually comes from. Again, it's always the same bond that we're going to break. We're going to break this bond here, and then we're going to remove this hydrogen here. And that's our H2O. So that is going to make our water. Now, if I separate this, let me go down here. I'm just gonna separate that. I'm gonna redraw this, but I'm redrawing it without the hydroxy group. And now I'm gonna redraw this without the hydrogen because we remove that to make the water. Well, now we have to bond this together. And I don't want there to be any confusion because some students, when we do this, is that um, they can't think three-dimensionally, and what they do is they end up drawing a structure like this, which makes absolutely no sense. So we're not going to bond it like that. So, right, that is not a structure we're going to draw. So what we do need to do is we're going to take, I'm going to take this structure here, I'm going to redraw this like this. All I've done was flip it around in three-dimensional space, and I've just kind of reversed it. And now we can see that this is where we're going to make our bond. So I'm going to draw the carboxylic acid without the OH. I'm going to draw this alcohol without the H. And then I'm going to make a bond from the carbonyl to the oxygen. And make a bond from the carbonyl to that oxygen. Let's see. Let's take another one. Carboxylic acid plus some alcohol I'm going to need some acid in order to do this. So one of the first products that we get is we're going to remove this here. We're going to remove this hydrogen here, and that's going to be our H2O. And real quick, I'm going to flip, because I removed that, I'm going to flip this around, and I'm going to redraw this way. So I have one. So all I've done was just flip that around. This way I can go ahead and attach it. So here's my carboxylic acid without that OH. And I'm going to redraw this down here. And then I'm going to make a bond from that carbonyl to the oxygen. So let me clean this up a little bit. 1, 2, 3, 1, 2, 3. There we go. Just kind of cleaned that up a little bit. If you drew it this way, it would still be the same answer. It really wouldn't matter. That's still the same answer, right? Is that these two here are identical, right? They're the same thing. Just one has a methyl up, one has a methyl down, but it's still the same structure. However you want to do that. Let's do, see, should we do one more at least? Carboxylic acid. Carboxylic acid. Carboxylic acid plus some alcohol. There it is. I'm going to remove this. I'm going to remove that hydrogen. We do need some acid for this to happen, but that is going to make my water. Let's redraw the carboxylic acid, but without that OH. So there, I've removed that OH, and I'm going to take this and I'm going to bond it to that carbon. And I have my ester, plus I get some water. I have my ester, plus some water. We have an ester, plus we have some water. And that's our process here. And that follows this here. So carboxylic acid plus alcohol, we get an ester plus water. And that's the same thing we've done over the last few reactions, is that we break it up, but we do break off that water in a certain place. Then it's definitely not just random there. So now let's do the reverse reaction, right? We need a carboxylic acid. We need a carboxylic acid, and we need an alcohol that's going to make this ester. Well, we know what bond we broke, and we know what bond we made here, right? Is that here we break off this hydroxy group. So the same bond that we broke, the same one that we made, is the same one we're going to break. So here, we're going to break it off at the carbonyl. And now I have these two separated. So let me go ahead and separate this. I have CH3, CH2, plus this carbonyl, and I have O, CH2, all right. Well, what we don't have here, remember this is plus water, it should be there, is that we're going to break this water up. And let me redraw this water here so we can have a little better understanding here. All right, we're going to break this up. Well, I need a carboxylic acid and an alcohol. Well, let's make our carboxylic acid, and then let's make our alcohol coming from that water there. And this is that reverse reaction, right? When we break an ester up, we get some carboxylic acid plus we get an alcohol. Here's my ester. Plus I have some water here. All right, so here's our water. We're going to break it off at the carbonyl, between the carbonyl and the oxygen. So I broke that off. So all I've done is separate these two. I've separated them, and I know that this water is also going to get broken up. I need a carboxylic acid, plus I need an alcohol. So ester gets broken up into a carboxylic acid plus an alcohol, and it is a reverse reaction there. All right, so we have esterification, right? And then we reverse that esterification. That's what's going to make that's what's going to make that alcohol and the carboxylic acid there. All right. So as far as naming our esters now, naming our esters is not going to be unfamiliar because we know how to name a carboxylate, right? Is it if I draw this here, butanoic acid, and I get butanoate. So we already know how to name these carboxylates. And let's take a look at this. Right, carboxylate. Oh. And we have a carboxylate. Right? So we know how to name these carboxylate ions already. So we're going to use that. And then we're going to name this branch here. So in order to name these, I'm going to draw some other lines here. I'm going to draw this right down here in the middle. Draw right down here. So we name the carboxylate. So here, 1, 2, 3. That this is propanoate. And then we name the branch. So the first half of the name is you're going to name the branch first, and then you're going to name the carboxylate. We name the branch first, and then we name the carboxylate. So methyl propanoate. 1, 2, 3, 4. 1, 2. So this is butyl acetate. We don't name it. It's not always right to left, left, right. If I reverse this and we draw a different structure, I'm going to draw a line right here. And here I have two branches. So here I have this branch, and then I have this carboxylate over here. So we're going to name this branch first, and then we're going to name this out. The portion with the carbonyl gets named second. The half with the carbonyl there it is. So the half with the carbonyl gets named second. The half with the carbonyl gets named second. The half with the carbonyl gets named second. So here we have ethyl, right? Then we're going to give it a space here. We have carbon 1, 2, 3, 4, 5. Ethyl, ethyl pentan O 8, because that's my carboxylate. Right? Let's go ahead and just split it off right here. The part without the carbonyl, the part with the carbonyl. So here I have isopropyl, carbon 1, 2, 3, propano 8, isopropyl propanone. Some more examples down here. So let's go ahead and split that off right here. This is going to be methyl. I named the part without the double bond first, the carbon, so the carbonyl here, and then I'm going to name this part. I go 1, 2, 2, 7. This is going to be carbon number 8. Do you see how I did that? There's 5 of these in here. There's 5 of those CH2s. So carbon number 1, carbon number 2. This is going to be carbon number through 7, and then I have carbon number 8 here. So this is going to be methyl octan O8. Let's divide this right here. This is ethyl. Butan O8. How about something like this? So here, 1, 2, 3. I'm going to name that half first, and this is propyl. And here I'm going to give this the common name. So commonly known as, right, there's one carbon there, so we use the prefix form, right? And we're going to call this form 8. Not formo 8, right? Formic. The IUPAC's naming uses the OATE, right? Here, this is common name, so formic acid, form 8. So let's just kind of review that here. There's formic acid. So formic acid to form 8, right? So differences between the common and IUPAC being. Let's see some more practice. So we're going to go ahead and separate this here. This is isopropyl. And here, it's not benzoic acid. We're going to drop the ic acid, benzo 8. So isopropyl benzo 8. Separate this here. This is going to be propyl. And this is 1, 2, 3, propano 8. So propyl, propan, O8. All right. Do you guys need a break? Yes.
I'm
No?
fine.
You're good? All right. So let's keep continuing. So we've named esters. We have our reactions with esters, esterification. And now we're going to do something we call acid hydrolysis. All right. Acid hydrolysis. So we know how to make an ester. In order to make an ester, that's esterification. We need a carboxylic acid, plus we get an alcohol, and that's going to make an ester, plus we're going to get some water. So the reverse reaction, we've already talked about this, but now we actually have the name for it. So if I go back up here, is that when we go back to this, right, what carboxylic acid, what alcohol required for this following ester? Is that we've already done these reactions, right? But now we're actually going to use an acid for this. So this is what we're going to call acid hydrolysis. Is we need some acid here, plus a little bit of heat, and this is going to be acid hydrolysis of an ester. And we get carboxylic acid plus an alcohol. In order to make the ester, alcohol plus carboxylic acid, we get the ester here. So we take a look at these reactions here. Right? We're going to break off. We're going to break it between the bond between the oxygen and that carbonyl, between the oxygen and the carbonyl. And then remember, our water also gets broken up. So let's go ahead and separate these, because this is going to be acid hydrolysis. So what we have here is we have CH3, CH2, my carbonyl, and that's where we split it off at. Plus, I have this oxygen, CH2, and the CH3, and now I'm going to add my water back into it. So I need, in order to, an ester breaks off into a carboxylic acid plus an alcohol. Carboxylic acid plus my alcohol. This next one, we're going to, we haven't even talked about that. Where did that reaction go? It's not in here, so let's go ahead and cover that bond reaction. So I don't know where that slide went, but we can still talk about it. So this is acid hydrolysis. So what we'll talk about now is there's also base hydrolysis of an ester, where we have some ester but this time we're going to add a base to it. So base hydrolysis of an ester. The same bond is broken, always the one between the carbonyl and the oxygen, and then we're going to remove this here. But instead of getting a carboxylic acid, base hydrolysis, because of this metal here in the base, we're going to get a carboxylate salt. And that's nothing new that we've seen. We've already seen this before here. So we're going to get plus our alcohol. All right, so let's look what an actual reaction looks like here. So here, let's give you an actual ester. All right, so here I have an ester. plus I'm going to add, let's use KOH. All right. So we break the bond, always between the carbonyl and the oxygen, and let's go ahead and split that up over here. So I've separated that, plus I've separated that, and then we're going to remove that hydrogen there. So base hydrolysis, we're going to get a carboxylate salt plus alcohol. If we're doing acid hydrolysis, carboxylic acid plus the alcohol. Base hydrolysis, we get a carboxylate salt plus the alcohol. So here we break that off. I'm going to put my hydrogen over here to get my alcohol, and then I'm going to get my carboxylate salt. So now we can take a look at that bottom reaction there. Is we're going to split off this here, and because this is base hydrolysis, and I'll even write it up here, so this is acid hydrolysis, and this is going to be base hydrolysis. Well, let's just go ahead and separate those first. So I have CH3, CH2, there's my carbonyl, plus I have my oxygen, all right. Base hydrolysis, what am I going to get? I'm going to get a carboxylate salt plus an alcohol. Well, there's my alcohol, and now I'm going to get my carboxylate salt. So this is our difference when we're doing base hydrolysis or acid hydrolysis to an ester. Acid hydrolysis, carboxylic acid plus an alcohol. Base hydrolysis, carboxylate salt plus an alcohol. Oh, let's see. Now we're going to, that's like actually just half the lecture. So actually not too much more. We've got to cover amines and amides. So amines are derivatives of ammonia. So here we see NH3 ammonia. But it's very easy to remove a hydrogen, and replace it with some alkyl group. Or remove another hydrogen, and then we have two alkyl groups. Or we can have three alkyl groups. And similar to our alcohols, we have primary, secondary, tertiary alcohols. Amines, we can do the same thing. Or I'm going to call them amines. This sounds pretty amine and amine. So I'm going to call it amine. So amines, and then we're going to talk about amides after this. So amines here, as far as a primary amine, let's give an example of a primary amine. Right? So this would be considered a primary amine because I have one alkyl branch to it. Another amine example. Right? It's not that I have two carbons, but I have one alkyl branch. So here is my, oh, come on. Here's my alkyl branch, right? Giving us another primary amine. And our secondary amine, you know what, one more example here, because we could also write it like this. How about, right? This is another example of a primary amine, because here I have one alkyl branch, right? I have an isopropyl attached. I have ethyl attached. I have methyl attached. So all examples of primary amines. Secondary amine is we're going to put two alkyl branches on it. So I have an NH. Let's put, how about methyl, or you can put two methyl groups on there. So there's a secondary amine. If we're using line formula, maybe I put an ethyl here, and let's put an isopropyl here, right? But we're going to count how many alkyl groups we have here. Two alkyl groups, secondary amine. Two alkyl groups, secondary amine. So our tertiary amine means that we're going to have three alkyl groups attached to it. They don't necessarily have to be the same. I mean, we could make them very different. How about I put, here's one alkyl branch, there's another alkyl branch, there's another alkyl branch. Again, this would be a tertiary amine, is that I have three alkyl branches attached to that nitrogen, giving me a tertiary amine there. So as far as naming our amines, well, we just name the branches in alphabetical order, and then we just attach the word amine at the very end. And notice that there's no space here. It is one word. So here we have a methyl, and then we say methylamine. Ethyl, ethylamine. Alphabetical order. Ethyl before methyl, ethyl, methylamine. All one word. Then if I were to do this, I have three different alkyl groups on here. Cyclohexyl, cyclopentyl, cyclopropyl. So here I have cyclohexyl, cyclopentyl, cyclopropylamine. One entire annoying word, right? No spaces between any of that. It's one word: cyclohexyl, cyclopentyl, cyclopropylamine. You know, and don't be shy from using these tries. We know how to name these branches. We know that there's three of them, so we could call it trimethylamine. Let's take one that has how about methyl, methyl, and an ethyl, right? So here I would have ethyl dimethylamine. And then we have our benzene derivative, aniline, right? So aniline is this structure here. And if I decide to put a branch on it, so these are something that you should already have aniline memorized. That if I decide to put, let's put an isopropyl here, is that carbon number 1 is where this functional group is at. So I have 3 isopropyl aniline. Three isopropyl aniline. All right. So again, this is a structure you should already have memorized and be able to recognize that. So not very complicated on how we name amines there. We just name the branches in alphabetical order, all one word, and at the very end of it, we just say amine.
Babooey.
And let's get some practice in here. All right, so here, right, here's our branch. This is, no, come on. cyclopentylamine. Carbon number 1, 2, 3, 4, 5, 6. So I have 3, 4 dibromo aniline. Here I have diethyl methyl amine. I notice I have one hydrogen here, which means that this is a branch. Yeah, this is also a branch. This is ethyl. 5 carbons. This is going to make carbon number 6. So this is hexyl. So we have ethyl, hexyl, amine. So different ways we can name them and recognize them. But if I see this one hydrogen here attached to that nitrogen, I know that this is a secondary amine. This is a tertiary amine. This is going to be a primary amine. Then we just recognize aniline as itself. Aniline being considered a primary amine. All right. So now reactions. Reactions based off of our amine. So know that ammonia is a base. Right? Ammonia is a base, which means water is going to act as our acid. So if this is our base, NH4 becomes our conjugate acid, and the OH is going to be our conjugate base. So ammonia is a base, which means that amines are also going to be bases because they're derivatives of ammonia. Is that here's ammonia, and these primary, secondary, tertiary amines are derivatives of ammonia, which means that they're also going to be bases. So bases, hydrogen acceptors, right? Bronsted-Lowry acids bases. So water is going to donate a hydrogen. The base is going to accept that hydrogen. So if I have an amine, well, the amine is my base. The amine is my base, and it's going to accept one of these hydrogens. So if it accepts one of those hydrogens, instead of NH2, it becomes NH3, and then we're going to add this little charge here. So NH3 plus, I'm going to get some OH minus, right? So this is how we're dealing with our reactions of amines when they're placed in water. They're going to form ammonium, some ammonium ion, plus we're going to get this conjugate base here. Right, so here's the reaction that we just did, right? And then we can call it, methyl ammonium, but I don't think we're not going to be tested on the names of these. Just a general reaction as far as these are concerned. So let's try a different one. How about let's use line formula. So here's my amine. plus I'm going to add some water. If this is my base, this is my acid. My base is going to be the hydrogen acceptor. So instead of NH, it becomes NH2. I'm going to put this little charge here, and then we'll put the rest of it back there. So I'm just going to add a hydrogen plus its charge, plus I'm going to get this hydroxide. Right. So that's our general reaction for putting an amine in water. So if we can put it in water, well, water acts as a base, but again, it's not. I'm sorry, water acts as an acid in this reaction, but it's not actually an acid, but it can act as an acid. So let's see what happens when we actually add an acid into or with an amine here. So we're going to get one compound from this. This isn't two separate compounds. So here we get our ammonium ion, plus we're going to get this base. Here we're only going to get one product from this. So let's give another reaction here. How about we have NH2 still, but let's put an ethyl on it. Clean this up. Plus I'm going to add an acid to it. And we're going to get this, let's see, ethyl ammonium, CH3, CH2, CH3, CH2. But instead of NH2, because this is my acid, this is my base, we're going to donate this hydrogen. So we get NH3. We'll put the little charge up here. And then all we have left is this ion floating around in the water. Well, notice this positive charge here, and that's why this chlorine is attracted to that. So this is the result of putting an amine with an acid. Let's try a different one here. How about there's my amine. Let's use hydrochloric acid. This is my acid. This is my base. I'm going to take this hydrogen. I'm going to donate it over here. So instead of NH, I'm going to get NH2. The ethyls go back on there, but I'm going to have this positive charge. This bromine with a negative charge is floating around in the water, so it's going to be attracted to that positive charge. And we can keep continuing on. I mean, it doesn't change the fact of what we're doing here. Here we'll go back to HCl. If this is my acid, this is my base. I'm going to take this hydrogen. It's going to donate over here. So instead of NH2, I'm going to get NH3, the positive charge. And then I have this chlorine floating around in the water, and that's going to be attracted to that positive charge. All right, and that brings us to our final group that we're talking about, amides. So we have amines, and then we have amides. So very similar to an amine, except we notice there's a carbonyl there, right? So this is our primary carbonyl. Secondary carbonyl would have this R group here, plus the R group that's on the carbonyl, And then we have our tertiary. So this is how we can differentiate between primary, secondary, tertiary amines linked to that. So let's draw some out here. I think maybe have some examples here, yeah? We'll go, there's more name. Let's go recognize some of these. So let me draw some out here. Right? There's an example of a primary amine. Secondary amines, I have an alkyl attached to that carbonyl. So let's draw something out here. I have my nitrogen, and I'm going to have another alkyl group here attached. Let's make it an ethyl, and then I have my hydrogen. Right? So we have secondary amine, tertiary amine,
Baba Booey.
right? And then we have our tertiary amine here. Let me. All right. So remember, and I'll just kind of recognize, I mean, that these are not carbons. It's, you know, countless mistakes made believing that those are carbons there. So, you know, those are not carbons. I just kind of want to reinforce that. So now as far as naming these amides, they take a little bit of extra work, right? So primary amides are relatively simple to name. Is that we're going to take the alkane name, whatever the alkane name is, and we're going to add amide to it, right? So here, 1, 2, 3, propane, we're going to drop the E and add amide, right? 1, 2, 3, 4. We drop the E, so this is from butane, drop the E, add amide. So propanamide, butanamide, but make sure you're not cutting off too much because this would get you an incorrect answer. It's not butamide. We've cut off too much, right? Is that we're only dropping that E and it becomes butanamide, propanamide, hexanamide. Eight carbons long. Octane, I'm going to drop the E and I'm going to add amide. So this becomes octanamide. Secondary amines. Secondary amines, because of this branch being on the nitrogen, instead of using a number, we're just going to actually add this capital N here to signify that we have a methyl group attached to our propanamide. So here is, right? Or actually, let me. Here. So there's our propanamide. And then on that same nitrogen where propanamide is that we have that methyl group. So this becomes N-methyl propanamide. Let's see, secondary. So if I were to draw something like this, right? Here's my branch that's on the nitrogen. 1, 2, 3, 4. So if we were just going to name this, and let me come back to this. So here, I'm just going to put this here. If we name this, well, this becomes butan amide. But if we actually make this into a branch, well, this is now an ethyl group. It's on the nitrogen, so we're going to label that as capital N, ethyl, and then we're going to use the rest of the name, butan amide. So N-ethyl butanamide. Remember this, 1, 2, 3. This is an isopropyl. It's bonded to this N, so I'm going to go N, isopropyl, pro, but I'm going to drop the E and I'm going to add ID. So N isopropyl propanamide. And now tertiary. Tertiary is going to be something similar, except each time that there's some branch on the nitrogen, we have to signify that with this N here. So here and here, I have two branches, and that's where we see this N-ethyl. N-ethyl. N-methyl. And then we have our propanamide. Right? 1, 2, 3, 4. We have a branch on the nitrogen, another branch on the nitrogen. This is isopropyl. This is methyl. Isopropyl comes first, so I'm going to write N isopropyl. I have another branch on the nitrogen, N methyl. Butan. I'm running out of room here. See if I can squeeze it in. There it is. So N isopropyl, N methyl butanamide. And if they are on the same branch, just like we have, if we were to draw this, so let me draw this out right here. Right, if I have something like this is carbon number 1, 2, 3, 4. Then we would go 2, 2, dimethyl. Well, very similar to that, we're going to, instead of saying 2, 2, we're going to go NN. Right? N, because both of them, they're the same. So we can do that. Up here, because they're different, we have to separate those. This is N-ethyl and methyl. But if I have two of the same ones, and it's dimethyl, then we can just simply put NN. So let's see. All right, now we'll use ethyl. So this can be N, di, ethyl, hexane, amide. Okay. So that's where we use the difference between N and here, and then this is N, and then the N is separated on the other side. So this is how we would name our secondary and tertiary amides. Here we have some more practices for us. So here, this is going to be cyclohexyl. It's sitting on the nitrogen, so I'm going to write N cyclohexyl. 1, 2. There's two ways we can name this. We can name it ethanamide, IUPAC, or N cyclohexyl acete, because there's two carbons there, amide. So N-cyclohexylethanamide, N-cyclohexylacetamide. Let's see here. What do we have? There's an isopropyl. All right, so we have N-isopropyl, pentan, drop the E, and we put amide. N-isopropyl pentanamide. And I think that brings us to just some final reactions. So reactions with amides. So these are what we're going to call acid hydrolysis, right? Because these amides and amines are bases, right? And they will react with strong acid. So if we have a strong acid or a strong base, is that they'll both react here when reacted. So one, if we take this amide and react it with a strong acid, you need to really memorize this. Memorize that when you have an amide plus an acid, you get a carboxylic acid and an amine salt. So we get a carboxylic acid plus an amine salt. So if we take some amide, add some water, add an acid, use a little heat, we get a carboxylic acid. We're going to remove this. We're going to get a carboxylic acid. Plus, we're going to get this amine salt. All right, carboxylic acid plus the amine salt. If we react it with a strong base, well, we have to memorize that we're going to get a carboxylate salt and some ammonia. Carboxylate salt and some, you could get an amine. I don't know if we're going to get that technical, but we could get either an ammonia or an amine. So let's give another, here's my amide plus my strong base. Let's use KOH. We're going to add some heat into that. We're going to get a carboxylate salt. There's my carboxylate salt plus some ammonia. So these reactions need to be memorized, right? You're going to get a carboxylic acid plus an amine salt if we use it. An amide plus an acid, an amide plus a base, carboxylate salt plus ammonia. Carboxylate salt plus some ammonia or an amine. So let's look at some more reactions here, right? Here I have an amine, plus I'm going to get an acid, which means I know that I'm going to get a carboxylic acid, plus I'm going to get an amine salt. Carboxylic acid, amine salt. All right, so let's get our carboxylic acid first. So we get our carboxylic acid plus our amine salt. There's our amine salt. Carboxylic acid plus our salt. Here's our carboxylic acid plus our amine salt. So you're going to want to really memorize these, right? Here I notice I have an amine or an amide plus I have a base. And what are we going to get from that? Well, we go back, we're going to get a carboxylate salt plus we're going to get either ammonia or an amine here. What are we going to get here? Looks like we're going to get an amine. So we're going to get our carboxylate salt. Means we're going to break this apart here. Let's get our carboxylate salt. There's our carboxylate salt. Plus, instead of going NH, we're going to get NH2. And this is our amine. Right? So from here, let's look at this one here. If we break this off, right, we get our carboxylate salt, this hydrogen, and that's where we get our NH3. This hydrogen, and that's where we get our NH2. So here we get a carboxylate salt plus our amine. Lots of reactions. All right, so that'll end Unit 9.